Hello everyone, I'm Xiong. Mm, Today I'll talk about our work Byzantine Lattice Agreement in Asynchronous systems. This is a joint work with Vijay Garg. Here's the roadmap of my presentation today. I'll first talk about the motivation, then go over preliminaries, and then summarize the related work and our results. After that, I'll talk about the basic idea of our order of log f errors algorithm with resilience f less than n over 5. And at last, I'll talk about some interesting future work. So the primary motivation behind the lattice agreement problem is its application in this special type of replicated state machine called update query state machine defined by Fedora et al. And in this type of state machine, it only supports update and query operation, but not update query mixed operations. So in one command, you can either have update or query, but you cannot have both update and query. And they assume that all updates are cumulative, which means the ordering of applying any two updates does not matter. Some examples include conflict-free replicated data types and atomic snapshot objects, etc. So we can use lattice agreement to implement this type of replicated state machine. And Fedora et al. They already have a procedure to do that, and 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 also we can achieve linearizability. Um, as we all know that for general replicated state machine, we usually use consensus-based algorithm like Paxos to reach agreement to to ensure a total ordering on commands. Uh, but consensus is impossible to solve in a synchronous system, even in the presence of one crash failure. Whereas lattice agreement can be solved in order of log f rounds. So if we use lattice agreement to implement and update query replicated state machines, hopefully we can get better performance. And another motivation of lattice agreement is its close relationship to atomic snapshot object. As shown by T et al., we can use lattice agreement to implement ASO and vice versa. We work in a completely connected message passing system of n process, and we assume there are at most f Byzantine failures, and Byzantine process can do arbitrary nasty things. And the system is asynchronous. The upper bound on message is not known by a process. We measure the round complexity of our time complexity of our algorithm using asynchronous rounds. An asynchronous round is composed of sending message to n process and wait for at least mlsf ACK message back and do some local computation. And the for communication, we assume the link is reliable. So in the lattice agreement problem, each process will have an input from a joint similarities. It is a partially ordered set that has a join for any non-empty finite subset. It can be denoted as the following triple. The first element is the set of elements in the lattice, and the second one is the order between the elements, and the third one is the join operator. Here is an example of a Boolean lattice. So the elements in this lattice are the power set of the universal set ABC, and the order between two elements are defined as a set inclusion, and the join operator is defined as set union. A chain in a lattice is a set of elements that are totally ordered. So in the Byzantine lattice agreement problem, each process has an input value from some joint similarities, and they must decide on some output value also in the joint similarities, such that it satisfies downward validity, which requires the output of each correct process has to be at least its input. And upward validity, which requires that Byzantine guys can introduce at most t values into the decision value of a correct process, where t is the actual number of Byzantine process in execution. The most important one is comparability, which requires for any correct pi and pj, their output yi and yj, either we have yi less than at most yj or yj at most yi. Here is an example of a possible lattice agreement execution. Suppose we have three processes, they propose A, B, C respectively, And one possible outcome is P1 decides on A, P2 decides on ABC, AB, P3 decides on ABC. Clearly, the output values are comparable and they form a total order. So now let's look at some of the related work and our results. In the synchronous model, if we don't assume digital signatures, and the best upper bound we know is the order of log f rounds algorithm with resilience less than f less than n over 3. And if we, under the same setting, if we assume digital signatures, the resilience can be improved to f less than n over 2. In the asynchronous model, that's the model we study in this paper. If we don't assume digital signatures, de Luna et al., they propose the best upper bound so far, order of f rounds algorithm with f less than n over 3, and they also prove that f less than n over 3 is the optimal resilience. And in this work, if we don't assume digital signatures, we propose an order of log f rounds algorithm with resilience f less than n over 3, n over 5. So we sacrifice the resilience a little bit, but we improve the time complexity exponentially. And if we assume digital signatures, we can improve our algorithm to have resilience of f less than n over 3. So now let's look at our order of log f rounds algorithm without the digital signature assumption. So in this work, I won't talk about the algorithm for with digital signature. You can go ahead and look at the paper. Suppose process can only have crash failure first. We'll deal with Byzantine failure later. And we use a high-level framework used by many previous work. So the basic idea is to design a classifier procedure that divides a group into two subgroups and ensure one group dominates the other. By dominate, we mean in the value of one group, the value of process in one group is at most the value of the process in the other group, which means one group is less than the other group. And then this classifier procedure kind of divide the overall problem into two subproblems, because at the current the classifier procedure guarantee the two groups are comparable. Then we can recursively invoke the classifier procedure. Specifically, we have to but the classifier procedure has to satisfy some properties in order to completely divide the overall problem into two separate subproblems. So the first property is we assume each process in the MEM algorithm. We assume each process holds a value set, and initially it's just its input, a synchronous set with its input. And for the first property requires the value set of each slave process is a subset of the value set of each master process. So basically, after say we have a group of process, after invoking the classifier procedure, within the classifier procedure, process will do some communication and in some ways, and they will update their value within the classifier procedure. So at the end, we need to guarantee the value set of each slave process is a subset of any value set of any master process. So for say 2, we need to guarantee the value set of each master process has more than k values. This k is a threshold parameter associated with a classifier procedure, and this is mainly used to guarantee that if we carefully set the threshold parameter, then we can guarantee the algorithm, the recursion terminates in order of log f rounds. And the third property is that the union of the value sets of all slave process has size at most k, which means there are at most k values in the value set of all slave process. So this is also used to guarantee the recursion. The recursive call can terminate in order of log f rounds. And so we call the one group as the slave group and another group as a master group, and we need to ensure the master group dominates the slave group. And okay, suppose we have such a classifier, so we can apply this classifier within each subgroup recursively too. solve the overall problem. And here is an example of such a valid classifier. Suppose we have for process each pi proposed vi, for instance, and the threshold parameter k is 3. So one possible outcome of the classifier is say p1 and p2 are classified as a slave, and p3 and p4 are classified as master. And for p1 and p2, their values stay the same, and for p3 and p4, they take the union of value received from p1 and p2, which is v1 and v2. So clearly the p1, the value of p1 and p2 are a subset of the value of p3 and p4. So if we recursively invoke the classifier procedure within p1 and p2, because by their decision value can be at most the union of v1 and v2, right? But for p3 and p4, if we recursively invoke the classifier procedure within the p3 and p4, then their decision value is at least v1 and v2, because they have v1 and v2 in common, and the property of lattice agreement needs to ensure that your output, your decision value has to be at least your input, right? Okay, so suppose we have such a classifier procedure, and now let's look at how we can how our main algorithm looks like. So works. So in the first round, we not let all processes exchange their values before recursively invoke the classifier procedure. So after this first round, each process has at least n minus f values and has at most n values, and then they invoke the classifier procedure in the way following the following binary tree. In the following binary tree, each node is associated with a classifier procedure, and if a process goes to a node, then it will invoke the classifier procedure, corresponding classifier procedure. Initially, all processes are located at the root node. They are within the same group, and the threshold for that classifier is n minus f over 2. You can see that this number is the mid value, is the mid of n minus f and n. So we set this number in a binary way. I mean, all the other threshold values of the classifier procedure in the binary tree are set in a binary way, so we can ensure that this tree has order of log f levels. And so at the root level, root node, they invoke the classifier procedure. If they're classified master, they go to the right, and if they're classified slave, they will go to the left. Yeah. And the properties of the classifier can guarantee that at the end of the algorithm, at the leaf level, if two nodes are located at different basically they're in different groups, then they must have comparable values by the property of the classifier. And if they are within the same node, we can ensure that they have the same value. So the main challenge caused by Byzantine process can be demonstrated by the following example. Suppose we have for process and pi proposed vi, and the threshold parameter case 3. Say we still one possible outcome of if we invoke the classifier procedure within this group, then p1, p2 are classified slave, and p3 and p4 are classified master, and they update their value in the way shown above. Yeah, and now suppose p2 is Byzantine, right? The classifier procedure can guarantee that they completely separate this p1 and p2 in a subgroup, and p3 and p4 in a subgroup, right? So they will recursively invoke the classifier procedure. But now suppose within group p1 and p2 is Byzantine, then what if p2 sends value v3 to p1 in a later level of the recursive call? Then p1 will take the union of v1 and v3, right? Because p1 kind of cannot distinguish whether p2 is Byzantine or not. So the best it can do is just take the union, and then in this case p1 will get to no value v3, and but you can say that for process p4, which is a master process, its value in its values v3 is not in its value set, and so for p4 its decision value might not include v3. Then in this case we break the property of the domination property of the classifier. So p1 is not P1's value is not the subset of P4's value anymore, right? So our main idea is to introduce the notion of miscible values for a group, which is basically the set of values that process in the group can ever have, and it's which is basically like after the classifier procedure, and there's a set of values that are the miscible values for the slave group, and it's like a upper bound, and the decision value of any slave process can be must be a subset of this set of miscible values, right? And so, and then our Byzantine tolerant classifier need to guarantee different properties. For B1, each correct slave process needs to have at most k values after the classifier procedure, and each correct master process has more than k values. And B2, this is the most important one and also the hardest one to guarantee, is the admissible values of the slave group is a subset of the value set of any master group process. So if we can guarantee this at the current level of the classifier procedure call, then because for the slave group, their decision value is always a subset of the admissible values, right? And we guarantee the admissible values is a subset of the value of any correct master process. Then if in the main algorithm, if we can ensure that for each process its value is non-decreasing, then we can guarantee the decision value of any slave process is less than is at most the value set of any master process, right? So that's the basic idea. And for B3, we need to guarantee that there are at most k values and in the admissible values of the slave group. And this is also used to ensure that there can be at most order of log f recursive call. So, and now let's look at our asynchronous Byzantine tolerant classifier. So in the classifier procedure, or in the main algorithm, each process stores a value set vi, and each process I also stores a safe value set. So this safe value set for each group, basically it's the set of values that will be considered as valid by process I. If process I received this value from some process in this group G. So this kind of serves as an upper bound. It limits the values that can be sent by a process. And process I will use this safe value set to filter out invalid values broadcast by process in this group. By the way, we use reliable broadcast to send values because we have Byzantine process. And so we define a value V is we say it's a miscible value for a group G if this value is in the safe value set of at least a quorum of correct process. So basically, this value has to be considered as valid by enough number of correct process to be an miscible value, right? So now let's look at the skeleton of the classifier procedure, how we guarantee those properties. So we had in the first round we have the right step. Each process will reliable broadcast its current value set to all and wait for acknowledgement from M-F process, and then after that process I will do a raise step. It reliable broadcasts a raise message to all, and wait for M-F process to send whatever the values they have back. So whenever a process receive a read message, they need to send whatever values they have, say reliably delivered back to this process, and then they do the classification based on the received values. If the received values is greater than k values, then this process is classified as master, and as a master it has to send a master messages again to all, and wait for M-F values. So basically when process receives a master message, it will send back their whatever values they have reliably delivered back to the process. And the master process, it will update its value set to be the union of all received values. Otherwise, if received at most k values, it is classified as a slave, and for the slave it stays its value set. It's the same. Basically, its output is also the same as its input for the classifier procedure. And Now let's look at how this classifier procedure can guarantee the three properties we define. For B1, we need to ensure the value set of each correct snake process has at most k values, and also the value set of each correct master process has more than k values. So this is obviously true based on the classification we do, right? If received more than k values, it's classified master. Otherwise, it's a snake. And for B2, we need to ensure the admissible values of the snake group is always a subset of the value set of any correct master process. So for the recall the definition of a admissible value, right? It is a admissible value if for a group G for the snake group specifically, if it is in the safe value set of at least a quorum of correct processes. So if you look at the code of the master process, after it is classified as a master, it will send a master message to read like MLSF values from back, right? And it's updated its value set to be the union of all received values. So in our algorithm, we can ensure that this MLSF quorum has an intersection with the safe value quorum defined for the admissible value. So in this case, we can ensure that for the master process can read all the admissible values for the snake group. Yeah. And for B3, there are at most k admissible values for the snake group. So in our case, we use this is guaranteed by the write step, the sequential execution of the write step and the read step. So consider the last process, slave process, possibly Byzantine, that completes the write step. It must have read all the admissible values of the snake group, because all the admissible values of the snake group can be at most whatever values reliably broadcast by the set of snake process, right, in the write step. So the last process which completes the write step must be able to read all the admissible values, and it is still classified as a slave. So it has at most then it has this set has at most k values. So for future work, we're interested in the lower bound for Lattice Agreement. There are no lower bound results at all for the Lattice Agreement problem, and we need to. So our conjecture is the order of log f is the lower bound. Yeah. And another interesting problem is how we can propose an order of log f rounds algorithm with optimal resilience f less than over 3. All right, that's it. Thank you.